Disaccharides are sugars that are composed of two monosaccharide units linked together through a condensation reaction. So condensation means loss of water during the reaction. The two individual units, or two individual monosaccharides, are thus bonded together through a glycosidic linkage. They can also undergo hydrolysis, which is the reverse reaction to yield their monosaccharide starting materials by boiling with dilute acid or reacting them, meaning the disaccharide, with the appropriate enzyme. Nutritionally, the most important members of this group are going to be mentioned in this video, and they are maltose. So we need to know maltose, lactose, and sucrose. And sucrose, you heard it before, is table sugar. All right, so maltose is also called malt sugar. It contains two glucose units joined together by a glycosidic linkage between carbon 1 of the first glucose unit and carbon 4 of the second unit. So you can see here we have carbon 1 of the first unit, carbon 4 of the second unit, and then they are linked together through this glycosidic linkage here, which we describe as alpha 1,4. And the reason why we do that is because the oxygen is beneath the first glucose ring, the one on the left. So the configuration is alpha, right? Because this is going down like this, right? Remember, down was alpha. And the symbol we use 1,4 because we're connecting carbons 1 and 4. So again, that's where the alpha 1,4 comes from for this glycosidic linkage. Now, maltose, which is found in germinating grain, is formed during the digestion or hydrolysis of starch, a polysaccharide to glucose. Its name is derived from the fact that during the germination or malting of barley, starch is hydrolyzed and the disaccharide is formed. On hydrolysis, maltose forms two molecules of D-glucose. And even though that reaction isn't shown here, it would just be the reverse of what you see here, right? If we went in the opposite direction, if we took our maltose, okay, just imagine we're going backwards here. And if we were to treat that with water and acid, okay, we'd go right back to our two original alpha D glucose molecules. And that's actually shown in 11.7 in the textbook. Now, maltose contains both an acetal carbon, which is on the left unit in position 1. So we have an acetal here, carbon, oxygen, carbon, oxygen, carbon. So this is an acetal and a hemiacetal at the first position, or carbon 1 of the glucose unit on the right. So we go oxygen, or hydrogen, oxygen, carbon like this. And so that would be our hemiacetal. So we have an acetal and a hemiacetal in maltose. So the presence of the hemiacetal group also means that the ring can open to expose an aldehyde group. And converting the hydroxy into an aldehyde is an oxidation. So something else must be reduced because oxidation cannot happen without an accompanying reaction. Thus, maltose is a reducing sugar. So if anybody ever asks you, is maltose a reducing sugar? The answer is yes, and it's because it contains a hemiacetal. And we said that hemiacetals would react with Benedict's reagent, which is proof that it's part of a reducing sugar. Lactose, or milk sugar, constitutes 5% of cow's milk and 7% of human milk by weight. Pure lactose is obtained from whey, the watery byproduct of cheese production. Lactose is composed of one molecule of D-galactose and one molecule of D-glucose. The linkage between the two sugars is beta 1,4 because the oxygen of the glycosidic linkage points up from the galactose ring. So the reason we call this linkage right here, we call this beta 1,4, right, is because this bond is going up, right? If it's in the up direction, it must be beta. So this is, again, a beta 1,4 linkage. And if you remember, the only difference between galactose and glucose was at carbon 4, the hydroxy or hydroxyl group on carbon 4 of galactose is pointing up, whereas in glucose, it's pointing down. Now, something else you probably noticed right away is that galactose contains a hemiacetal shown right here. And so since it has a hemiacetal, that means the lactose is going to be a reducing sugar. All right, so this is an interesting problem. 11.8, gentobiose is a disaccharide formed when glucose is caramelized by heating. Describe the linkage between the two components. So if we number our carbons in the molecule on the, or the portion on the left-hand side, we have 1, 2, 3, 4, 5, 6. And on the one on the right, we have 1, 2, 3, 4, 5, 6. So we can see that our linkage is 1, 6. And since this bond here is pointing up, that means it is going to be beta. So this must be a beta 1,6 linkage. The disaccharide sucrose, or common household sugar, is extremely abundant in the plant world. It occurs in many fruits, the nectar of flowers, and in the juices of many plants, especially sugarcane and sugar beets. Sucrose contains two monosaccharides, glucose and fructose, joined together by a linkage that is alpha from carbon 1 of glucose and beta from carbon 2 of fructose. Now, if you study the structure of sucrose, which is shown here, okay, if you study it hard, you'll notice that the molecule contains neither a hemiacetal nor a hemiketal group that is necessary for ring opening because both anomeric positions are part of the glycosidic linkage that links both rings together. So this is in contrast to maltose and lactose, where both rings are locked in the cyclic form in the case of sucrose, whereas in maltose and lactose, the ring on the right-hand side is not locked in the cyclic form, and therefore sucrose is not a reducing sugar. And so you need to remember that. So I wrote it down here. So out of all the disaccharides that we've studied, um, sucrose is the only one that is not a reducing sugar. Maltose and lactose are both reducing sugars. And so if we look at the summary of the disaccharides we've covered in this video, which are maltose, lactose, and sucrose, maltose is formed from the glycosidic linkage formed between two glucose units, and the linkage is alpha 1, 4. When we look at lactose, it's formed between galactose and glucose, and the linkage is beta 1, 4. And then when we look at sucrose, there's two glycosidic linkages, aren't there, right? And you can see they're both highlighted here. We have the alpha one, the alpha one, and then we have the beta one here. The reason I call this one alpha is because it's going down, and this one's beta because it's going up. But either way, you can see that both anomeric carbons are tied up in these glycosides, and so that means that sucrose is not a reducing sugar.